Okay, this is a video for AP test review number 9, and what I did is I took like an old AP test question 2016. I kind of modified it a little bit just so I could ask a few different questions. So anyway, the first one is they give you some rate law data is kind of what this is, and they want you to calculate the initial pressure for trial 1. Okay, so they give you the temperature. What you can get from the graph. The first one is concentration versus time. Well, at time 0, the initial concentration right here, you can see that that's 0.020, and the units are moles. So there's that many moles in 1 liter. Now, that will help us because when we do this gas pressure that we're trying to get here, we're going to have to use the PV equals nRT, which is a very common thing that they have you do on the AP test. Anyway, so we want to get what P is, okay? V, do we know V? Well, you can get the V from the molarity because it doesn't come right out and tell you what the volume is, but because you know the molarity, you can just say, well, we know that we'll just say that there's 1 liter. So we know that the volume is 1 liter equals N. Okay, well, we know the moles that are in that 1 liter, 0.020 moles. Okay, times R. Okay, now it wants it in atmosphere, so we got to use the one. It will be on your AP formula sheet, 0.08206 atmospheres times liters divided by moles Kelvin. And then we got to take that times the temperature. Remember, in gas laws, your temperatures have to be in kelvins, which this one, they were nice enough and gave it to us like that already. But the gas law constant tells you what unit everything needs to be in. All right, and so then you solve all this, divide by 1 liter, and you end up getting that if you round it off, it turns out to be about 1.0 atmospheres. All right. Okay, question number 2. Use the data in the plotted graphs to determine the order of the reaction with respect to C4H6. So if you go back and look at the graphs, you can see that if you had a straight line, if this was a straight line, but it's not, it's a curve, that would be 0 order if the concentration over time is a straight line. If natural log of a concentration over time is a straight line, it's first order. And if you look, this one is the 1 over the inverse of that. And so then this ends up being second order. So that's how you can tell it's second order. All right. So it's second order. Okay, calculate the initial rate of the reaction. The initial rate is something. Calculate the rate constant for the reaction at 625 Kelvin. Okay, so you can get the initial rate by taking the rate law, which is rate equals K, and it's going to be C4H6, and that's going to be to the second power because it's a second order reaction. Okay, now they're giving us the initial rate, so we'll just plug that in, 0.0010, and they give us the units, which is molarity per second. So the units, I like to combine these two units just to make it easier and call it molarity seconds to the -1. That just makes it easier to deal with. Molarity seconds to the -1. That's going to be equal to K. And then we got to find what the initial concentration of in trial 1, like what the initial concentration was, and we just did that in a previous problem. We looked up the initial concentration, and it was 0.020 molar is what the concentration was. So we're going to multiply that times 0.020, and it's going to be molarity but we have to square it according to the rate law. So then if we just move the math around and solve, like basically square this and then divide both sides by it, we end up getting K is equal to 2.5. But now the units are kind of tricky because when you move this 0.02, so you're going to have this like 0.0010 molarity seconds to the -1, and you're going to be dividing that, and I didn't calculate the number, but it's 0.020 molarity squared. Well, basically, you're going to have a molarity to do exponents to the first power minus a molarity to the second power. And so basically what you end up getting is you get 2.5 molarity to the -1 power, because a molarity divided by a molarity squared, you subtract the exponents. Seconds to the -1 still stay how they are. Okay, that's going to be the rate constant. Okay, now at some point, and this is where I kind of made up this problem here. This reaches equilibrium. This problem is not part of the 2016 test or whatever, but I just made it up, and it's just to give you a little practice with Le Chatelier's principle. So when you're dealing with pressure and things like that with Le Chatelier's principle, I like to think about drawing a particle diagram. And so this is the C4H6 side. So C4H6, and there's 2 moles. I'm getting that from right here. And then we have C8H12, and there's only 1 mole of that gas. And so I'm getting it from the number in front here, C8H12. Now, a lot of times, okay, so if the volume of the container is increased, so if the volume is increased, so if the volume of the container goes up, that means the pressure is going to go down. And what will happen is this reaction will shift, okay, one way or the other to make that pressure go back up. So if the volume of the container was increased, the pressure is going to go down. So this reaction is going to shift to make it go back up. Well, what causes more pressure? 2 moles of gas hitting the side of a container or 1 mole of gas? Okay, the answer is 2 moles of gas striking the side of the container. So this one's going to shift to the left, because if it shifts left, there will be more moles of gas to strike the sides of the container. All right? Okay, this one, silver nitrate. Let's see. Okay, silver nitrate reacts with 100 milliliters of 2 molar mercury chloride and precipitate forms. Okay, identify the precipitate. Well, they're telling you that these are AQ, so that's AQ, that's AQ. Okay, now we gotta know something over here, and I forgot to write the 2 there. Okay, so silver nitrate, all nitrates are AQ. That's one thing AP wanted you to memorize. That means the silver chloride must be the precipitate. So silver chloride is a precipitate. Okay, write the net ionic equation. Okay, anything that's AQ on both sides is going to cross off. So the nitrate, and so we have 2 silver plus 1 ions, AQ, plus 2 chloride. Now there's this 2 here, 2 chloride, -1 AQ, gives 2, oops, I need to go back, that's not what I want, 2 silver chloride, solid. Now the 2's all cancel, and then you just get Ag plus 1 plus Cl minus 1 gives AgCl. Now some people like to write Cl2, and they make that mistake right here. So an easier way I feel to write a net ionic equation when you're doing the precipitation ones is take the precipitate and write it in its without the number in front of it. So AgCl solid. And then you just think, well, hey, what ions do I need to make AgCl? Well, I need Ag plus 1, AQ, plus Cl -1, AQ. Then I don't have to worry about, like, do I bring this 2 down or put it in front and cancel them all out? If you just work backwards, this is a much easier way to do it sometimes, I feel like, on the precipitation ones. Okay, after the reaction is complete, calculate the number of milliliters of excess reagent. Well, we have equal amounts and they have equal molarities. But what I would look at then is say, well, hey, you need twice as much silver nitrate as HgCl. So anyway, so I know that silver nitrate is going to be the limiting reagent. And so I'm going to start off my problem, or you could probably just do this one in your head, but I'm just going to start it off and do it. So I got 100 milliliters of AgNO3, and I'm going to take the molarity, 0.20 moles AgNO3 for every 1,000 milliliters of it. Okay, so doing that math right there gets me into moles. Then comes the mole ratio. 2 moles AgNO3 to 1 mole HgCl2. Supposed to be a C. Okay, mole ratio from equation. Then I'm going to use the molarity. So 0.20 moles is the molarity of the HgCl2. Now, a mistake that a lot of people make is in this is the molarity step. You got to put 1,000 milliliters right here. Okay? Not 100 milliliters. That's how much you have, but this is like figuring out how much you're going to use. A big mistake is some people would put 100 there. Okay, so you're going to use 50 milliliters of the HgCl2. Now that's how much you're going to use. How much are you starting with? You're starting with 100 milliliters. So 100 milliliters minus 50 milliliters equals 50 milliliters. Now, it just so happens, this is maybe a bad question, that this answer and this answer are the same. But don't forget that this is calculating how much you're going to use, not how much is left over. So you always got to subtract it from what you start with. Okay, so that's an important step right there. Okay, draw a particle diagram representing the species and their relative ratios at the conclusion of the reaction. Okay, so here's my big beaker here. Okay, so we've mixed them all together just like the problem said. And so now I know at the bottom I have this precipitate, which is AgCl solid. So that's at the bottom, okay? Now, what we know though is there's going to be some mercury. Okay, so there's going to be some mercury. So for every 1 mercury, okay, there's going to be, and there was supposed to be a 2 there, there's going to be 2 nitrate. So for every 1 mercury, there'll be 2 nitrates. Okay, now what some people might forget is that also this was in excess. So there's some of this also remaining. So you would need some mercury again, but you're also going to need some excess chloride. And for every 1 mercury, you're going to need 2 chlorides. All right, so that's how that would go. All right, don't forget about the excess. That was kind of the point there. All right, last question. Okay, write the equation showing the dissolution dissolving a calcium chloride in water. So let's say we have calcium chloride and it's a solid. Okay, just omit the water on these dissolving ones. Okay, and so then we get calcium is going to break into ions, AQ, and chloride, Cl negative 1, AQ. We'd put a 2 in front of there. All right. Now, okay, the KSP of calcium chloride equals 1210 at 25. How would the KSP change if the temperature was raised to 100. Okay, remember that the KSP would be equal to the concentration of the calcium ion times the concentration of the chloride ion to the second power. That's what the KSP would be equal to. Okay, now it's also telling us that this is an exothermic. So if it's exothermic reaction, the kilojoules would be on this side of the arrow. Now, if you're raising the temperature to 100, so the temperature is going up, okay, that means that you're adding kilojoules to this side. It's going to make it shift to the left. And if it shifts to the left, it's going to make fewer of these ions in solution. Fewer ions of these in solution would make your KSP get smaller because there's fewer ions because it's going to shift left. Okay, that's it for this video then.